yeah, right now. So it's recording now, and yeah, we'll get into like the fun stuff, the chemistry. All right, so starting off with significant figures, it's kind of like, I guess like a bombastic name if you use that word a lot. Like it sounds a lot more imposing than it actually is, because actually most people like to call it sig figs. Yeah, you will have access to the presentation after class. I can even here, we're gonna do breakout rooms in a little bit actually. So I'll send the slides to you right now. So I'm just gonna pause sharing so I can send these. Yeah, because when we go into breakout rooms, I'm pretty sure you won't be able to see my screen anymore. So it'll definitely be good for you to have.
I can just upload the presentation to Google Classroom right now.
Oh yeah, all right, cool. I kind of have the link copy, so I'll just send it in the chat too. But either way, you guys will have two ways to find it. Okay. Yeah, so back to significant figures. We actually just call them sig figs, or like everybody calls them sig figs, because like the nickname suggests, they're not that big of a deal. It's just a way for us to get more familiar with how to round correctly. Like obviously everybody here knows how to round, but depending on like how you measure things, there's like a certain amount of decimal places you need to go to, or it's not necessarily always about decimal places too, but we'll try to make it a little bit clearer. So basically, like you have a number, and then in that number, a certain amount of those digits will be significant and some won't be significant. So there's a couple rules that like surround it. So all non-zero digits are significant. So like, say I have just like 1, 2, 3, 4, that has 4 digits. And because all of them are non-zero, it has 4 significant digits. So that one's like really easy to know. And then the second rule is that zeros in between significant digits are always significant. So basically, if I just like stem off of 1, 2, 3, 4 for a second, if I have like 1, 0, 0, 2, 3, 4, if we look at the first rule, all non-zero digits are significant. So we have 4 non-zero things. So that'd be 1, 2, 3, 4. And then zeros in between significant digits are always significant. Basically meaning that since we found these zeros in between the 1 and the 2, they have to get counted as significant figures. So that would mean that we have 1, 2, 3, 4, 5, 6 significant figures in that particular number. And then a couple more rules. Zeros that do nothing. This is a little bit of my own phrasing since it's kind of unscientific to say do nothing, but it's how I like to think about it. Zeros that do nothing but set the decimal point are not significant. So like you can see this number. It's not that the zeros on the number aren't doing anything. It's just that you're going up in orders of magnitude, right? So if I compare like 4,700 to 47,000, here, I'll put the commas to make it a little bit more clear. The only difference between these two numbers is multiplying or dividing by 10, right? All you're doing is adding or subtracting a zero. So that's what I mean by like the zero not doing anything. You're not necessarily changing the value of the number more than you are just scaling it up by a factor of 10. So it works the other way too. So if you're thinking about numbers less than 1, so like 0.003 and 0.0003, even though they're apart in value by 10 times, they both only have one significant figure. And it's the 3 in both of them, because all these zeros do is just tell you how much smaller it is than the other one. So in the case of 4,700, 470,000, or 47,000, all of those would have two significant figures because of the 4 and the 7, which are non-zero. There are some cases where zeros that look like they're not doing anything are significant though. So I guess that phrasing might be a little bit tricky, but here I'm going to move this. Yeah, so you can see how I have this example here. 4.00 has 3 sig figs. So you might think it's 1 sig fig because you have a 4 and then it kind of looks like these zeros are useless. But, people are pretty lazy, right? So they wouldn't just add on zeros for the fun of it. Everything that looks useless but is added on has a meaning. Like it's there for a reason. So basically, as we're about to learn, how many like decimal places you have will impact your final answer in terms of how you round it. So the fact that this person chose to put 4.00 instead of like 4.0 or 4.000 has like significance. Like this will have 3 significant figures. This will have 2, and this will have 4. And the reason that they don't like do nothing, like in this case, is because these are the same number in like magnitude, right? Like 4 is 4 is 4. Whereas like up here, they were different by like a factor of 10 each time. So I guess that's one way that you could think about it. So like that's how you would count significant figures, right? So I don't know if our breakout rooms are ready yet, but we have a couple examples here. Once again, my screen's not going to like appear on your screen once we go into breakout rooms. So if you have the presentation pulled up yourself, it'll be really helpful. But basically, when we go into breakout rooms, we just want you guys to like, I guess, first of all, introduce yourselves to each other just so that you have like a quieter environment or like a more intimate environment to like get to know each other. And then try and work through these 2 example problems where basically all we want you to do is count how many significant figures there are in each number. So like this is number 1 and this is number 2. Wait, Ria, are breakout
You want me
rooms
to
working?
create them?
Yeah.
Yeah, they are.
All right.
Okay. Go ahead and join your room.
All right, and feel free to tell us if like something went wrong and you didn't get assigned or something, or if you just want to stay in here and like do it with us, I guess.
Oh, she must be having tech problems.
Yeah, there's 2.
Yeah. Do you want me to just like move you myself? Because I can do that manually.
Yeah, because I got kicked out. So
Okay. Yeah, I'll just assign you to room 5.
thank you.
All right, yeah, that's good.
Yeah. So do you want to just move to different breakout rooms and then we can...
Yeah, that's a good idea.
I think it's 1-0.
I think that the first one has 3 because 3.24 is the same thing as 3.240, and then the 0 is not really significant.
Well, any zeros. Supposed to do.
So we're just supposed to figure out the significant figures. So like for the first one, I guess.
I think first one is 4.
Yeah, it would be 4 because there's the 3, 2.
Yes, it has the 3, 2, 4, and then the 0 at the end is a sig fig because it's
added on.
added on.
Hey everybody, how's it going? Anything?
Yeah, we finished the first 2 questions.
Oh, cool. What'd you answer?
So the first one was 4 sig figs. The second one was 2 sig figs.
Oh, nice. All right, cool. Just curious, does anybody like have chem experience from school? Or is this just like something you've done outside, or maybe you're just getting started?
I've done like some chemistry experience outside of school.
Mm-hmm. Okay. All right, well, good job on getting the right answers. I'm gonna go check on other people. See ya. All right, right now we're just kind of waiting for everybody to like trickle back. But from what I saw, like going into a couple of rooms, it seemed like everybody was pretty good, like on the right track. So I'll just like go over the answers really quickly. Once everybody gets back, we're like a third of the way there. Hold on. All right, we've got almost everybody back, so I'll start explaining the answers just in case you guys were a little confused. So the easiest rule to remember, if anybody remembers, was that anything non-zero is always significant, right? So we're always looking for non-zero digits first. And it's pretty easy to see that we have a 3, 2, 4 in the first number. So we have 3 already, or 3 sig figs already. We just have to determine if 0 is significant or not. So we either have 3 or 4 basically. And then here we have 2 already because of the 9 and the 1. And then here we're figuring out whether these zeros are significant or not. Pretty much all the time, zeros are going to be like where you're iffy at sig figs until you just get a little bit more comfortable with it. So on this side, on the left side, so the 0 actually does end up being significant. And if you remember like the examples from the past slide, it's because 4.0 versus 4.00, like I said, humans are lazy. They wouldn't do something for no reason, right? Everybody wants to be as efficient as possible and spend as little amount of time as possible on something, right? So if you could just call a number 4, you wouldn't say 4.00. So the fact that they are saying 4.00 means that they're trying to communicate something. They're doing it for a reason. So that's why 3.24 versus 3.240, you're counting different amounts of sig figs here, because even though it looks like the 0 isn't contributing any sort of value or like any sort of magnitude, they put it for a reason. So you would actually count this trailing 0, that's what you call it, trailing, as a significant figure. So +1 equals 4 sig figs. And then on this side, I think the example we used was like 47,000 versus like 4,700 and like 470,000. In this case, we're not comparing numbers that have the same magnitude, right? They're different by a factor of 10. And for that reason, even though it's a little bit harder to see because this is a decimal, but if you compare it to like 0.00, I'll put the 0 so it looks the same, 0.0091, this is still different by a factor of 10. So the zeros basically, like I said in the last slide, aren't doing anything. And you're comparing numbers that are basically different in magnitude, but they look similar just because they're different by 1 magnitude of 10 or 1 0. So in this case, these zeros aren't significant, so you would stop counting at 2 sig figs. All right, I think everybody's back. All right, yeah, so we can move on. All right, so basically the first part of sig figs is learning how to count how many there are, right? But then after that, there are arguably more importantly, the rules on like how to combine, because the whole reason that sig figs exists is because you need to know how to round in like a professional setting, basically. Because if somebody tells you like put 12.4 milliliters into this beaker of like whatever liquid you're working with, you want to know if that is exact or not. You want to know how much it's being rounded by. You basically want to have a feel for how accurate that is, or actually how precise, not accurate. But because you want to know basically whether there's any uncertainty involved. So that's why we use sig figs. So we learned how to count, and now first we're going to cover addition and subtraction. They go by the same rules because subtraction is like negative addition, basically. And addition and subtraction are, I would say, arguably easier than the multiplication and division rules. It's basically that you compare your two numbers and then you look at the accuracy of the less accurate number, and then you apply that to your final answer. Like when I said that, it sounds kind of obscure, right? It's hard to understand, but I think this example helps. So when you're dealing with decimals, as you usually will be in chemistry, sorry, could you mute yourself? I think I'm echoing, thanks. Yeah, so when you're dealing with decimals like 101.5 and 1.555, you first need to look at the accuracy of the two numbers. So 101.5 goes to the tenths place, and then 1.555 goes to the thousandths place. So when you're adding the two numbers, the less accurate of the two of them is the one that goes to the tenths place, because the more decimal places you have, like the more detailed the number is, right? So you want to pick the less detailed number and then use that as your benchmark, sort of. So if you're not rounding and you're just adding them up, this is your answer, right? 103.055. But because you have to apply sig figs here, you make it match the place of the least accurate addend. So in this case, that would be using the tenths place. So if you're rounding 103.055 to the tenths place, you would do 103.1 because you have that 5 in this place. Yeah, I hope we don't need to teach how to round. I think we're going to be fine though. Yeah, so that's basically how you do addition. It's a little bit more complicated. Oh, let me see what's on the next slide. Oh, practice. All right. It's a little bit more complicated when you're not dealing with decimals though, because if you're dealing with like 101 versus like 2020, if we like look at the accuracy, 101 is accurate to the ones place, right? Because we have a 1 here. But 2020 is only accurate to the tens, because in the ones place we have a 0, and basically if you were counting the sig figs here, this would have 3 sig figs, right? So this 0 is not significant, so you can only say that it's accurate to this last 2 here. So if we're adding, this is without sig figs, so I'm not rounding. 1, 2, 1, 2, right? Pretty easy. But from here, we need to apply sig figs. And because 2020 is our less accurate number, we need to be basically rounding to the tenths place. So our answer actually becomes 2120 because it's accurate to the tenths place, because the 0 isn't telling us anything. It's just scaling up by a factor of 10. But you really shouldn't encounter that kind of scenario in chemistry just because it's pretty much rooted in smaller numbers that have decimal places. So it should be much easier. But you will get to, like, I guess, exercise that on this first problem. Not really so much on here though. I didn't have a subtraction example, but you do the same thing basically. You look for the accuracy of the two, you determine which one is less accurate, and then you just do the subtraction and then round to the less accurate place. All right, so let's see if we can go in breakout rooms again. Yeah, actually we might have to have it set up so that we can just have breakout rooms continually running, and like you can just go to the one you were originally in or something.
Yeah, let me see if I can set that up.
All right, go ahead and join everybody.
I'll close the rooms after 4 minutes. How's that?
All right, yeah, cool. All right, we got a couple of pretty fast people. Oh, by the way, I'm assuming like you guys are back because you did it already. So if any of you like have access to the annotate feature and you wanted to just like, I guess, draw out how you did it, feel free. Yeah, nice. I like the way you show it with the underline. All right, seems like people are coming back. All right, yeah, I'll get started again. So if you weren't here to see that like demonstration, basically how Sarath did it was basically I'm pretty sure everybody adds like this, like you just put the numbers on top of each other. And at first you just like add regularly. So you get 10,060, right? But then you have to apply your sig figs afterward. So you're looking, I mean, you're basically counting sig figs, but you can just look for the least accurate digit. So here, your least accurate digit is 4, which is in the hundredths place, or hundreds place, not hundredths. And the reason it's the least accurate is because you have zeros following after it, and they're just, they're not exactly trailing, but they're just there to scale up by a factor of 100. And for the same reason, your least accurate place in 660 is the rightmost 6. So here, that means when you apply sig figs, you're going to have to round to the hundreds place because it's less accurate than the tens place. So that becomes 1,000 or 10,100 once you're done. And here, once again, just like writing it out. So 1, 4, 0. I don't want to like accidentally forget how to subtract, but all right, yeah. So that would be like your exact answer. And then this time it's a little bit easier because you have decimals, right? So your least accurate one in 592.67 is in the hundredths place, and your least accurate one in, or I guess it's your most accurate place, but in 101,629, you're in the thousandths place. So the less accurate one in between these two is the hundredths place. So you want to round your final answer to the hundredths place. So 491.04. Yeah, so now we're going to follow up with multiplication and division. It's like kind of similar, but it's definitely not as intuitive, I guess. You basically have to count, actually. So for multiplication and division, it's not really about decimal places anymore, like it usually was for addition and subtraction. You actually have to count the number of sig figs in each of the numbers that you're either multiplying or dividing, and then same concept applies how you use the least number of sig figs, and then you apply that to your final answer. So if we take the example of 52.7 and 63, if we're just counting sig figs, these two numbers are like really easy because they only have non-zero stuff. So this says 3 sig figs, this says 2. So if you're doing 52.7 times 63, you're multiplying a 3 sig fig number by a 2 sig fig number. So your answer has to has 2 sig figs because basically like you're taking the accuracy of your least accurate like multiplied number in this case. I don't know why, I just forgot what the term was, but basically the least accurate number between 3 and 2 is 2, so your final answer has to have 2 sig figs. So if you multiply it out exactly, you get a 5 sig fig number. Obviously, it's too precise, so we need to round it. And the way to get this rounded to 2 sig figs is to have your front two numbers be significant and then just zeros on the end. Same thing with division. Just like how I called addition, just like how I called subtraction negative addition, division is basically like inverse multiplication, right? So for division, what you would do is you divide the two numbers. You get your exact answer at first, or like a repeating number, I guess, if it's like 0.3 repeating. And then what you would do is you'd compare how many sig figs each, like the dividend and the divisor have. And then you would use the less accurate number. So basically the lower number, because it's all positive numbers that we're dealing with. So I don't know if the breakout rooms are still open, actually. Sorry, I don't have access, but yeah, there we go. So go ahead and try to figure it out with your group. Feel free to like write on the screen in case you haven't figured out the annotation thing yet.
Hey Bradley, do you remember what room you were in before?
I was in room 4. Sorry, I'm kind of having like difficulties because I'm on my phone and I'm trying to get home. I'm biking home, so like I'm having a little bit of trouble.
You're totally fine. I just didn't know what room you were in.
All right, thank you.
Do you think we're going to get through the entire presentation by the end of class?
I think not the periodic table stuff. So I can like put that on the end of, or in the beginning of number 2 and push some stuff from number 2 into number 3. Because
I might have to readjust, maybe take out a unit.
Yeah.
Just so we can get through everything, because class is moving slower than we expected.
I think we can definitely get through like slide 17 or 18 though, just not like getting too far in depth into periodic table.
Yeah, it's fine. We can do that.
All right, cool. If any of you guys are like confident in the way you solved it, feel free to annotate like last time. This time, if you do though, like try to leave your work on the screen so I can like use it as an example, just in case like you found a cool way to do it. Or I can always just annotate myself. Hold on.
Also, when you guys are done discussing in your rooms, feel free to leave the breakout room. It'll give me like a heads up on just who is done.
All right, almost everybody's back, so I guess I'll start explaining. All right, I mean, the first example is pretty easy because there's no like iffy stuff with the sig fig counting. This has 4 and this has 2 because there's no zeros to be worried about. I mean, oh, okay, this has 3. I don't know, it just went through my mind. All right, so between 4 and 3, the less accurate one is obviously 3. So our final answer is going to have 3 sig figs. So obviously for this part, you can use a calculator. You don't have to like do mental math or like make a table or whatever. So the exact answer comes out to 19,940.58. Obviously, this has way too many sig figs. There's 7 in there, and we need 3. So in order to shave this down to 3 sig figs, what we're going to do is we just go the first 3 like digits of the number, and then we satisfy our 3 sig figs. So we literally just put 0, 0. And that's our answer for this one. Division, like I said, it's pretty much the same thing as multiplication. So here, once again, calculator. So this one, I don't think it comes out to something exact, but I'll just list out like a bunch of stuff. So like this is as far as we need to go, because if we look, this has 4 sig figs because all 4 of these digits are non-zero. And this has 5 sig figs. The reason being that this 0 is between significant digits because 8 and 1 are both significant. So since this 0 is like sandwiched by them, it counts as a significant digit. So between 4 and 5, 4 is the lesser number. So our final answer is going to have 4 sig figs. So remember that any zeros that are like in the decimal point, but that come before your number, like don't count basically, like they're not significant. That changes if like instead of 0.0 whatever, you have like 2.0 something, then the 0 counts because it's in between significant digits, right? But oops, hold on, let me write that out again. But if you have 0.0 something, the 0 after the decimal point is not significant. So here, like I said, 4, 5, so we're going to the less accurate 4. You just basically list out 4 significant digits until I guess you don't want to go over, but you list out 4. So here, the reason that it's not 6 and that it's 7 is just because you would round at the 100,000th place. All right, so yeah, not too difficult or anything. It's just like a foundational skill that we needed to know. So the big takeaway from all of this is that you don't want to be rounding too much, right? Because in a chemistry problem, or at least like a decently complex chemistry problem, you're going to need to do like multiple calculation steps in order to get to your final answer. So if you're rounding at each step and you're like shaving off stuff to make sure that your sig figs match, you're going to end up getting like a flawed answer that's kind of off. So what you should do is obviously you're using a calculator. So store the number in your calculator or just like press the up arrow and then like press enter so that the number like falls back down. So you're using as many decimal points as possible just so that you're using it as accurate or precise as a number as possible. And your final answer is when you want to be applying sig figs, not in between or intermediate answers. All right, so now we're just going to be covering like a little bit more foundational stuff, I guess. This one is just like, I guess, hitting the highlights. So for units of measurement, there's not very many things that we measure in chemistry. but we just wanted you to be familiar with all of them so nobody was confused when we went ahead in the future. So first, there's mass. I'm sure you guys know that's like the amount of matter something has, right? Or like if we're talking physics, like the amount of inertia it has. So that's measured in grams. In chemistry, you probably won't really see kilograms because like that's kind of a huge scale to be working on, especially since a lot of stuff in chem is expensive. So like having a kilogram of like gold is kind of a lot. Amount is measured in moles or MOL, which is like the shortened version. Don't worry if you don't know what this is yet. We're going to cover that next week. It's basically like a roundabout way to say how much mass of something you have too. Volume is measured in liters, but you'll more likely see it in milliliters just because, like, once again, the scale is kind of huge if you measure in liters. Temperature, we like to use Kelvin, which is on the same scale as Celsius, as in like 1 degree Kelvin is the same like magnitude as like 1 degree Celsius. I like to think of it as like width, as if you're on like a number line, like it's the same width. But the only difference is that Celsius is scaled 273.15 degrees higher. But anyways, we like to use K. Pressure, you'll see like ATM usually since we're in America, but like the international people like to use bar. They're pretty similar measurements actually. They're only a little bit different. And then there are a couple smaller measurements like millimeters of mercury, which is what mmHg is. And then there's also torr, which is like, once again, basically equal to mmHg. And concentration and energy and like voltage and stuff, we don't really have to worry about until later. I'm pretty sure like a lot of us know this, but I'll just go over it because some of the like bigger or like less familiar prefixes are like kind of hard to memorize. So you've heard of like gigabytes before. Basically, like a gigabyte is 1,000 times larger than a megabyte because like a megabyte has 1,000,000 bytes, right? And a gigabyte has 1,000,000,000. So like you can think of like bytes, I guess, as a way to think about like the big prefixes. So like giga is capital G, mega is capital M. And that helps when you're dealing with like, yeah, that's a more eloquent way to say it. Like an increase of 1 Kelvin is equal to an increase of 1 Celsius. Yeah, but anyways, you can just like refer to this chart anytime you run into like something unfamiliar, because I'm pretty sure like none of us have worked in like femto before. You might see pico, but like femto, it's kind of rare to come around. Okay, this will probably be like our last topic, just because like we wanted to cover the basics once again, and then we'll get into like chemical equations and like stoichiometry on Wednesday. So that's 2 days from now in the next lesson. But just covering scientific notation, basically you have this like absurdly long number, right? And you don't want to waste time, like I was talking about earlier, just saying 0, 0, 0, 0, and so on. So how you would want to express this is by isolating the non-zero stuff and then just multiplying by a power of 10, which looks a lot simpler and definitely does not waste as much of your time. So when you isolate the non-zero stuff for scientific notation, you want it to be, I was gonna say a 1-digit number. It's not really a 1-digit number because you might have like decimal places on it, right? But the stuff before the decimal point or to the left of the decimal point has to be 1 digit when you're doing scientific notation. So even though this is equal in magnitude to 62.4 times 10 to the negative 14th, this is like not how you would say it in scientific notation, because you want to express the non-zero stuff in a way that the number is smaller. So it's in between 1 and 10, basically. So for numbers under 1, like if you're looking at an absurd number like this and you want to like express it in scientific notation, what I like to do is I just like to count the zeros. So like if I count in groups of 3, for example, 3, 6, 9, there's 12 zeros here. And what I do with like that knowledge is that I know that there are 12 zeros. So if I add 1 onto 12, it's 13. And then this is a number that's less than 1. So the power of 10 has to be negative. So I have 6.24. That's the non-zero stuff. And then I had 12 zeros plus 1 is 13. So it's 6.24 times 10 to the negative 13th. So that's like, I mean, not even really a shortcut. That's like how you're supposed to do a number is less than 1. And then for larger numbers, I guess depending on what type of person you are, this might be easier or harder for you. But once again, set aside the non-zero stuff. Make sure it's in between 1 and 9.9 repeating. And what you want to do is kind of counting the zeros again, but not really, because here there's obviously 6 zeros. But what you want to do is you want to imagine that everything after the first non-zero thing is a 0. So imagine that this is 600 million instead of 624 million. You would have 8 zeros, right? So basically that would mean that your power of 10 is 10 to the 8th, and then you would just substitute in the non-zero stuff. So basically 6.24 times 10 to the 8th. All right, I think we're gonna be wrapping it up around here for today. Let me check if we're missing some important stuff. Here, I'll cover slide 17. Slide 16 is not really that necessary, but you can look at it on your own if you want. Basically for slide 17, all you need to know is that there's 2 big things in chemistry. Mass is always conserved, number 1. So if you think about like burning wood, you might just think it disappears, right? But actually what's happening is like it's letting off carbon dioxide gas and like water. So like the mass is going into the air, even though it looks like it's disappearing. And the second big thing is that energy can't be created or destroyed, only transferred or transformed. I'm pretty sure you guys all know this too. But, you know, think about that thing with the roller coaster on the hill. When it's at the top, all the energy is like potential, right? And then when it's at the bottom, it's converted to kinetic. But you can't just like randomly put in energy from nowhere. So yeah, go ahead. That's just like 2 main things to remember that'll help you with problem solving later on. Yeah, all right. We're gonna cut it off here for today. Like I said earlier, we're going to get more into like the chemistry of stuff next week. So that'll be like chemical equations, stoichiometry, basic reactions, and we'll also cover like the periodic table since we didn't get that today. But yeah, hope you guys have a good day. Make sure you like eat dinner if you're on the East Coast. All right, see ya.
Yeah, and we'll be sending out a form. Look for it on the Google Classroom. It's just a quick quiz and then like some feedback from you guys on how this lesson went.